On example 5, we want to integrate. We've got x minus 2 over x squared plus 4x plus 3. Integrate with respect to x. So notice, of course, that the degree of the bottom is 1 smaller than the degree of the top. So it is in the kind of form of the one that we were just working with, which was like this one here, right? We have linear on top, we have quadratic. And whenever we did our partial fraction decomposition, we ended up something that was logarithmic, right? It's a du over u. That's kind of the goal here with this partial fraction decomposition, to turn it into that kind of thing. And that's going to happen if you have quadratic on the bottom, its derivative is linear. But if you try to do a u substitution, it doesn't exactly match up. U would be equal to x squared plus 4x plus 3, and then du is equal to 2x plus 4, which now, okay, then that is a clue that we should try to do partial fraction decomposition. All right, so ignore the calculus for right now, and we have to do the algebra necessary to decompose this into its partial fractions. So I'm going to rewrite just the rational function down. And then remember, first step is to factor the denominator. So factoring the denominator in this case should be really easy. I'm going to just rewrite the top down. All right, we've got an x times x. We're supposed to multiply up to 3, add up to 4. It's a plus 3, a plus 1. It really doesn't matter which one comes first. Okay, over here on the right side of this equation, we're going to rewrite it so that these are the denominators of our two partial fractions, and we just don't know what the numerators are supposed to be. Okay, and now what we do is we multiply both sides of this equation, of course, by the common denominator, and the common denominator is just this product here. It's the same thing as this quadratic that's on the bottom. And so that I can have some extra room here, let's go ahead and delete this so I can write this thing down. Multiply both sides by x plus 3 times x plus 1. All right, obviously on the left side, the denominator cancels out, right? All of this. Where's the cancellation crank? Come on. All of this will cancel out with each one of these factors, leaving me with just x minus 2. Okay, on the right side of the equation, when I multiply these factors times a over x plus 3, the factors of x plus 3 are going to cancel out, leaving me with just an x plus 1, which I'll multiply times the a. And then finally, when I multiply or when I distribute this to the second term, the last one here, b over x plus 1, obviously the factors of x plus 1 are going to cancel, and I'm going to be left with b times x plus 3. And you can see in these very, very simple ones that essentially the two denominators just switch places. Okay, so now we have our basic equation. So basic. And we're just going to choose some super convenient x values so that we can make either the a or the b disappear. Let's start here with this one. It's very simple. What can I let x equal? How about x is equal to -1? So everywhere there's an x, you're going to substitute in a -1. We're going to have on this side a -1 minus 2 is equal to, when I plug it in here, I'm not going to bother writing this down because I know this is going to go to 0. That's the whole reason why I chose it. And then b times -1 plus 3. We have a -3 on the left is equal to a positive 2b, meaning that b is equal to a -3/2. All right, well, we got some sort of fraction this time. Totally okay. It often happens. All right, so I'm going to come back to my basic equation. This time we need b to disappear, so the convenient value is going to be x is equal to -3. And plug in -3 everywhere we have an x. I get -3 minus 2 on the left side. A times -3 plus 1. And I don't have to bother with this second one because it's going to disappear. It's going to cancel out. Why am I changing colors? Don't know. Negative 5 is equal to a positive 2a, meaning that a is equal to negative 5 halves. All right, so I have my two numerators, and I want to rewrite it, and make sure that you rewrite it in the correct order. The a, the negative 5 over 2, has to go on top of the x plus 3. Don't mistakenly put it on top of the x plus 1. Okay, so our integral becomes something far, far simpler, even though it has fractions in it. I've got a negative 5 over 2 over x plus 3 plus a negative 3 over 2 over, wait, is that, was it correct? Oh, you know it wasn't correct. You were probably screaming at me and I just didn't hear you with these headphones that I've got in. When I subtracted this right here, negative 3 plus 1 should have made that a negative 2. When I divide, that should make this a positive. Ha 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 ha. Okay, so then this one's positive. Got it. I got it. All right, I fixed my mistake. Everything is right with the world, and this one is x plus 1, I think. Yes, dx. Okay, so each one of these becomes a u substitution, right? It's a very simple u substitution, one that we really won't have to fix. U is equal to x plus 3. du is equal to dx, so there's nothing to fix there. Likewise, on the second one, u is equal to x plus 1. Its derivative is just dx. There's nothing to fix here. So both of these are just straightforward applications of the logarithmic antiderivative. Yeah, okay. So we're going to carry over this 5 halves times the natural log of the absolute value, don't forget it, x plus 3, minus 3 halves, natural log absolute value of x plus 1, and then plus c. It's entirely possible that these are combined. You can bring these 5 over 2 and 3 over 2 in as exponents, and you can do the subtraction as a quotient. Sometimes, though, on the answer key, on the multiple choice answers, it's just left expanded like that. That's very convenient, so it's done.